cubic graph is a graph of the form y equals ax cubed plus bx squared plus cx plus d, where the numbers a, b, c and d are all real numbers, and we will need a to not be 0 so that we do have a power 3 for x in the expression. So a cubic graph is a graph with an x cubed term and possibly powers of x lower than that as well. We need to investigate what these graphs look like. Let's start with the simplest possible case. Y is x cubed. If we've never seen a graph of this function before, we can start off by plotting some of the points that it passes through and deducing what its general shape is. So let's just look at a few x, y coordinates. If we have x values of 0, 1, 2, 3, etc., the y values that go with those will be 0, 1, 8, 27, cubing the x value in every case. We can see the values of y get large quite quickly for the corresponding values of x. So let's plot a few of those points. As expected, we're going to get some sort of curve which increases very rapidly. There's no need for us to restrict ourselves only to positive values of x. We can also investigate what happens for negative values of x. In every case, the magnitude of the y coordinate will be the same, but for negative values of x we will get a negative value of y. For example, if x is negative 1, then y will be negative 1 times negative 1 times negative 1, which is negative 1 rather than positive 1. We can now see the shape of the curve that goes through these points. Here is the shape of y equals x cubed. When we were looking at parabolas, the graphs of quadratic functions, we found that they all had the same shape as a basic graph of y equals x squared. However, in the case of a cubic graph, that's not going to be true. Here's the graph of y equals x cubed. If we're interested in the graph of y equals ax cubed plus bx squared plus cx plus d, the values of a, b, c and d can make significant differences to the shape of this graph. Here's the one that we've just looked at with an a of 1 and a b, c and d of 0. By allowing the values of a, b, c and d to vary, we can start to see a large number of differences to the way that this curve can look. How are we going to be able to tell these situations apart? And how are we going to be able to decide how to draw the graph of any given cubic equation? We'll investigate this using some examples. In this example, we're asked to sketch the curve of the equation y equals x plus 1, x plus 2, x minus 2. The fact that this is already factorized will make our life quite easy. Let's return to some of the ideas we had when we were sketching quadratics. Firstly, we can find the intersection points with the axes. To find the intersection point with the y-axis, we need to put x equal to 0. So if we put x equal to 0, then we have a y of 1 times 2 times negative 2, which is negative 4. So we know that this cubic will pass through 0, negative 4. To find the intersections with the x-axis, we need to put y equal to 0. If y is equal to 0, then that means that x plus 1 times x plus 2 times x minus 2 is equal to 0, and so it's easy to see that either x is minus 1, or x is minus 2, or x is 2. So therefore we have these intersections with the x-axis. Negative 1, 0, negative 2, 0, and 2, 0. Another thing we can do is to consider the behavior of this curve as the value of x gets larger and larger towards positive infinity, or in the other direction, smaller and smaller towards negative infinity. We can say that as x gets larger and larger, and the way we'll do that is to say as it gets closer with this arrow to infinity, what happens to y? Well, if x is a large positive number, then x plus 1 is a large positive number, and so is x plus 2, and so is x minus 2. The fact that we've taken 2 off a very large positive number is not going to make much of a difference. So we will be multiplying together 3 large positive numbers, which will give us a large positive value for y. In other words, as x tends to infinity, y also tends to infinity. What happens as x tends to negative infinity, as it gets smaller and smaller, going down the number line in the opposite direction? Well, in that case, x plus 1 will be a very large negative number, x plus 2 will be a very large negative number, x minus 2 will be a very large negative number. So we will be multiplying together 3 large negative numbers, which will give us another large negative number. So as x tends to negative infinity, y will also tend to negative infinity. Intuitively, what this tells us is that as we go further and further in this x direction, the curve will move further and further down in this direction. In other words, when we're sketching it, it will sort of come in from the left from down here. Similarly, as x gets larger and larger in the positive direction, so does y. In other words, as we move towards the right, the curve will head off up towards the top right. How can we also deal with the fact that the curve must pass through all of the points we have found earlier? We will need a curve which has this shape. This fits all of our information. The curve comes in from the bottom left and goes off to the top right. It cuts the axes in the required places, and you will see later in the course that it will be possible for us to show that a cubic curve like this can have at most 2 points where it reaches maxima or minima points, so there can't be any more up or down changes than we've drawn here. In general, we will see that cubics have these sorts of shapes in most cases. We also saw that our original x cubed graph looked like it was going to turn around, leveled off, and then changed its mind and carried on back up again. It will even be possible for this curve not to quite level off and then continue to carry back up. In this example, we have to sketch the curve with the equation y equals x times x plus 3 times 1 minus x. So we'll start with the same steps. When we have an x of 0, that means we have a y of 0 times 3 times 1. Well, that is still 0. Therefore, this curve passes through 0, 0. When we have a y of 0, that means that x times x plus 3 times 1 minus x is 0. So therefore, either x is 0, x is negative 3, or x is 1. So the curve passes through 0, 0, which we did already know about, negative 3, 0, and 1, 0. Now let's investigate the behaviour as x gets very, very large and positive. As x tends to infinity, what happens to y? Well, the x will get very large and positive. The x plus 3 will be very large and positive, but 1 minus x is 1 take away a very large positive number, which will therefore be negative. So we will have the product of 2 positive and 1 negative number, which will therefore be negative. So the y in this case gets closer and closer to negative infinity. Similarly, as the x gets very, very large but negative, tending towards negative infinity, the y will be the product of one very large but negative part, another very large but negative part. Here we will have one subtract a large negative number, so this part will be positive. So we will have a negative times a negative times a positive, which will be positive. So the y will get very, very large and positive. It will tend to infinity. That means that as x comes in from the left, from negative infinity, we will have a positive y. And as the x gets larger and larger towards positive infinity, the y will be negative. So we have the opposite situation from before. Our graph will start up here and finish down here. Let's see what all that information would look like. We have our points of intersection, and combined with our information about the behavior of the graph as x is very large and very small, we will end up with a curve that looks like this. Although the curve is very similar in many ways to the one from our first example, there's a little bit of reflection in the x-axis going on here in terms of what its behavior is as x tends to plus or minus infinity. To go with the shapes we saw in the first question, we'll also have these possibilities, that the curve may do something like this, or be like our original x cubed graph, but in reverse, or be the version where it doesn't quite level off before going down again. In this example, we have to sketch the curve with equation y equals x minus 2, x plus 3 squared. Well, a lot of the ideas will be very similar. When x is 0, we will have a y of negative 2 times 3 squared, so that will be negative 18, and therefore we know this passes through 0, negative 18. When y is 0, we have that x subtract 2, x plus 3 squared is 0, so therefore either x is 2 or x is negative 3, so we pass through these points on the x-axis, 2, 0, and negative 3, 0. Oops, missed out the equal sign there. But it is important to note that this negative 3, 0 is what we call a repeated root, in that it appears twice. We have x plus 3 times x plus 3. As x tends to infinity, the value of y tends to positive infinity. As x tends to negative infinity, y also tends to negative infinity. Now, I did those a bit quickly. We could go through the same steps we did in the first place, investigating whether we're multiplying positive or negative pieces together. But you may have noticed by now that we can tell this straight away by just looking at the coefficient of x cubed. In other words, if we had expanded all the brackets and we had some x cubeds, and of course also some x squareds and some x's and a number on the end, it is the value of a that determines the shape of the curve. If we have a positive coefficient of x cubed, then we have this kind of shape, or possibly without the up and down motion, but you get the idea. If a is negative, we will have this kind of shape. So putting that information together, we have the following intersection points. Together with our general knowledge about the shape of the curve, how can we fit a cubic through these? You'll notice something significant straight away, which is that the repeated root, the negative 3, 0, is a place where the curve just touches the x-axis rather than cutting through it. If the curve did cut through both of these points, then it would have to cut through at a third place to maintain the general shape of a cubic. So it must touch at just one of them, and it is the repeated root where it does that. In this example, we don't just have a double repeated root, we have a triple repeated root. Let's go through our normal stages. If we have an x of 0, that will mean we have a y of negative 3 cubed, which is negative 27. So we have an intersection point of 0, negative 27. If we have a y of 0, then that means we have x subtract 3 cubed being 0. In other words, x is 3, and we have an intersection point with the x-axis at 3, 0. But this is only one intersection point. We also know, because the coefficient of x cubed is positive, that our cubic will either have this shape or this shape. or this shape, how can we determine which of the three it is? Here are our intersection points, and our cubic curve will look like this. How can I be so sure it has this shape of all of the possibilities? Well, suppose we have started off with the cubic curve that we know well. How could we get the one that we are trying to sketch from that curve? We can do it by replacing x by x subtract 3, which we know from our transformation work is the same thing as doing a translation of 3, 0. In other words, if we start off with our y equals x cubed graph and then translate 3 places to the right, we will end up with the curve that we are interested in. Here is an example where we have to do a bit more work ourselves. Sketch the curve with equation y equals 4x subtract 3x squared subtract x cubed. Because this is not factorised, it's quite difficult to understand some features of it. So let's see if we can do any factorising ourselves. If y is 4x subtract 3x squared subtract x cubed, then by factorising an x out of this, we can see that that is y is x into 4 subtract 3x subtract x squared. And maybe we can factorise this piece on the end as well. I'm not quite sure if we'll be able to or not, so why don't we just quickly check its discriminant, which is negative 3 squared subtract 4 times negative 1 times 4, that is 9 plus 16, which is 25, which is 5 squared, so it's a square number, the discriminant. We will be able to factorise. Oh, I don't like the look of factorising in that form. It will help us a lot if we also factorise out a negative 1. So now it will be in the form x squared plus 3x subtract 4, and that leaves us in a much better situation to try and factorise on site. And it is not difficult to see that it is x plus 4, x subtract 1. So now we can do all the stages that we would normally do. If x is 0, then y, it is easy to see, is 0. This curve will pass through 0, 0. If y is 0, it is easy to see that x is either 0, that's the point we already know about, or x is negative 4, or x is 1, so it also passes through negative 4, 0, and 1, 0. We will have a negative coefficient of x cubed, so it will have this kind of shape. Let's put all of that information together. We have our intersection points. We don't have any repeated roots, so this curve will not touch the axis, it will cut through at these 3 points. And because we also know about its general shape because of the coefficient of x cubed, we will have a curve that looks like this. Remember that when we were sketching quadratic graphs, we were also finding the coordinates of the vertex, the maximum or minimum point on the curve. And in a cubic like this, we have one minimum and one maximum point. However, we don't have the same amount of symmetry that we had with a quadratic curve, so there's no easy way at the moment for us to know exactly where those points are. So if you are doing sketches like this, you will not be required to include scales on the axes or know exactly how far up or down the curve goes. It's the general shape and the intersection points which are important at this stage. This example is partially factorised for us. Sketch the curve with the equation y equals x squared plus 2x plus 2 times x plus 2. What about that quadratic term? Could we factorise that any more? I'm not quite sure. What's its discriminant? The discriminant of that quadratic factor is b, which is 2 squared, subtract 4 times a, which is 1, times c, which is 2. That's 4 subtract 8, which is negative 4. Right, that's not a square number. A negative number could never be square because the product of two numbers, whether positive or negative, could not be negative. So therefore this quadratic cannot be factorised. In fact, it has no solutions, even if they're not nice whole number ones. There will be no other place where this curve cuts through the x-axis from the quadratic factor. What do we know? We know, as usual, that if x is 0, we can find a y value, which in this case will be 2 times 2, which is 4. So the curve does cut through 0, 4. If y is 0, we know that can only be because x is negative 2 from the linear factor. We've already established that the quadratic factor, because it has a negative discriminant, has no solutions. Therefore, negative 2, 0 is another intersection point. We also have a positive coefficient of x cubed, therefore our curve will have this shape, or maybe this shape. What can we actually deduce about it? Well, here are our intersection points. Unfortunately, in a case like this, we just do not have enough information to be particularly conclusive. Here is one possible curve that goes through those points and has the correct behaviour as x tends to plus or minus infinity. We may have one of these curves which doesn't level off at any point at all. But here is another curve which fits all the information we have perfectly well. It's an important skill to be able to recognise when you do have enough information to be conclusive about the curve, or whether there is still a bit of ambiguity. So let's sum up with our general method for sketching cubic graphs. First, we find the point of intersection of the cubic with the y-axis. Then we find the point or points of intersection of the cubic with the x-axis. And unlike the case of parabolas, there always will be a point of intersection of a cubic with the x-axis if the curve either begins from the bottom left and ends on the top right, or starts at the top left and ends at the bottom right. It must cut through the x-axis during that journey at some point. We also have to identify the nature of the intersections with the x-axis, since there are several ways in which this can happen. If we have single roots which are not repeated in a factorisation of the cubic, then the curve will cut through the x-axis at those points. This was one of our examples when that happened. Each of the intersection points were roots which occurred only once in the factorisation. If we have double roots, ones which are repeated twice in a factorisation, then the cubic will touch the x-axis at that point. Here was an example of that, where the root x equals negative 3 occurred twice in our factorisation. If we have a triple root, one which is repeated 3 times in the factorisation of the cubic, then the cubic graph will cut through the x-axis at that point, but it will do it tangentially. It will level off to have a gradient of 0 at the point where it cuts through. Here is our example of that. Because the equation was y equals x minus 3 cubed, the point 3, 0 is a point where the curve cuts through the x-axis tangentially. And we also have to determine the general shape of the curve from its behaviour as x tends to infinity and as x tends to negative infinity. But we know that we can do this by looking at the coefficient of x cubed. If we have a positive coefficient of x cubed, we have a curve with this general shape. If we have a negative coefficient, we have a curve with this general shape.